Hi, and welcome to the Physics 3 Tutor Volume 2. Now, in this course, we're going to continue right where we left off in the end of the Physics 3 Tutor Volume 1. You know, there's a tremendous amount of material that you need to cover in order to really understand electricity and magnetism. And in the first DVD in this sequence, the Volume 1 of Physics 3, we covered a tremendous amount of ground. We covered, what is an electric field? What is an electric force? How does it arise? We talked about using Gauss's law to calculate the electric field. We talked about the electric potential and how it kind of relates to our concept of voltage that we've kind of, hear in everyday language, right? We did a lot of calculations and talking about when things are spherically symmetric, when things are cylindrically symmetric, when things are planarly, have a planar arrangement. And we used Gauss's law extensively to talk about calculating the electric field in those cases. And along the way, we got comfortable with the concept of the electric field and so on, and the electric potential. Now in this course, in this section, in this volume, we're going to continue that journey. We're going to obviously need everything that we've learned before. So if you haven't viewed that, you need to stop now and go back and review that because it's a building block process. You have to know one thing before you move to the next. In this section, in this volume, we're going to continue and we're going to talk about the more practical side of how do you use these things. Capacitors. We're going to talk about capacitors. We're going to talk about what the electric field is inside of a capacitor in an electric circuit. We're going to talk about electric circuits and resistors and figuring out what the electric current really means, what the voltage really means. How do we calculate those quantities in an electric circuit using our knowledge that we've already gained from understanding what an electric field really is. And then we're going to move on toward the end of this volume to some more advanced topics here before moving on to the next topic, into the next volume, where we're going to really hit the magnetic field and begin to tie electricity and magnetism together into one nice, pretty package. But you can't do that too early because you can't really tie electricity with magnetism until you really fully explore what each of those topics are. And so we're building our way to that process. So enjoy the course. We're going to take it one step at a time. We're going to work a lot of example problems to make sure that you're comfortable. And so by the end of this, I promise you, if you stay with me on this journey, you'll understand it, you'll do well on your test, and I think you'll have a really great appreciation for how cool this stuff really is. So here we're going to talk about the concept of capacitance and what is a capacitor. Capacitor, you've seen them before in your life. They're in every little circuit that you see. If you open your computer case up and look inside your computer and look at the circuit board, you'll see capacitors all over the board. If you open up a radio, you'll see capacitors all inside of a clock radio. So capacitor is one of the three or four big, components that you have, in a circuit that really can make electrons come alive. But before you can really understand how to use them, it's really instructive to know how they're constructed, what they do, and a little bit of the theory behind it. And so that's what we're going to talk about in this section on capacitance. So briefly, let me read you a little definition, and I'm going to write it up on the board for you. Basically, a capacitor stores charge. It's a charge reservoir. It lets you, it's sort of a vault that you can put inside of an electric circuit. You have a battery in a circuit, and battery supplies electric current. And we're going to draw pictures of circuits and all these things coming up. But from your basic experience that you have batteries and they store electric charge, and they deliver the charge to whatever's in the circuit. Well, a capacitor is sort of like a temporary battery. It's like a temporary charge reservoir. So you can use the battery to charge up the capacitor, and then you can take the charge out of that capacitor later. And you can kind of take money out of the bank, so to speak, in terms of electric charge. And we'll see that there's a little bit more to it than that, but that's the basic idea of what a capacitor is. It stores charge, and anytime you have charge present, net charge, positive or negative charge, you have electric field present. So there's going to be an electric field inside of this capacitor that's going to be always present anytime the capacitor has charge. And so that's why it makes sense to introduce capacitance now, because we just talked about the electric field in great detail. Now we're going to show you a practical device that you use in every circuit. This microphone here, the video camera, anything has a capacitor in it, and we're going to show you a practical demonstration or sort of a discussion of how the capacitors work and why they're useful. And then in the next few sections, we're going to talk about circuits with capacitors, and then we're going to move on into some other topics related to circuits as well. Okay, so let's talk about the concept of a capacitor. Capacitor, right? It has a sort of a lengthy, scary sounding definition, but it's exactly what I told you. It's sort of a charge reservoir. So it's a device in a circuit. I mean, a capacitor really doesn't make any sense if you just put one on the board here. I mean, it has to be hooked into a circuit to do something. So it's a device in a circuit that stores electric charge, right? So you can almost think about it like a battery. They're different though. I mean, a battery has a chemical reaction and they're generating these electrons that come out of the battery into your circuit. A capacitor is a passive thing. There's no chemicals in it. It's just that it's sort of like a bank vault. You can put money in the bank in the form of electric charge, and then the circuit can pull the charge out. And so it's really good for oscillating circuits where you're like maybe trying to build a radio, where you have an oscillating wave coming in. It's putting money in the bank, taking money out of the bank. I'm getting ahead of myself a little bit, but capacitors and later on inductors we'll talk about are really used quite frequently in oscillating circuits, and we'll talk about all the reasons why. So it's a device that stores electric charge. Let me write one more thing I didn't tell you. So I'm going to take this period off. Stores electric charge that allows the capacitor, and I'm going to just call it the cap, the capacitor. You're going to see me write that out a lot. When I say cap, it means capacitor, just as an abbreviation, to store energy as potential energy. You know, I'm going to draw a lot of pictures here in a second, but you know, it's good to see things in words. So let's read this real quick. It's a device in a circuit that stores electric charge and it allows the capacitor to store energy in the form of potential energy. So it's basically a device that you can basically use to store electric charge. Now when you think about it, and we're going to draw a lot of pictures here in just a second, so don't feel like if you don't quite understand what I'm saying, we're not going to talk about it more, because we will. But when you think about it, anytime you have charge present, you know, like we talked about in free space in the last volume, you have an electric field. And we talked a lot about the electric potential, and we talked about the fact that this field, just by the virtue of it being there, sort of has energy associated with it. In other words, it has the potential to do work, because if I have an electric field here and I take a charged particle and I put it in the field, what's going to happen? It's going to begin to move. And that doesn't come from nowhere. It comes from the fact that the field is doing work on that charge. Just like if I push something, I'm doing work on that charge or that massive object or whatever it is. So the electric field can actually do work, and so we say that it has energy associated with it. I mean, otherwise, how would it do work? So it has to have energy associated with it. It has potential energy. It's the same thing as a rubber band. You stretch a rubber band, you can think of that like an electric field. And if it's always stretched, it always has potential energy. Now, at the moment that you decide to let it go, that potential energy begins to be used. Well, an electric field always has the potential to do work, but it can only do work on charged particles, on particles that have an electric charge on it. So if this capacitor stores charge, we'll talk about drawing some pictures in a minute, and if those charges that are in there sort of set up an electric field inside this capacitor, then it stands to reason that that capacitor must be a sort of like a storage device for potential energy. And that's why it's useful, really. And the details of the circuit theory of why you would use them, and we're not going to design radios in this course, but I'm telling you as sort of like an advanced preview that when you get into oscillating circuits, you might be oscillating and dumping electric charge in and out, in and out, in and out. You might be trying to generate a wave to be sent as a radio wave, for instance, or any number of other reasons that you would use capacitors. But that's basically sort of a preview. So it's a storage device. It stores the charge, and because of that, it's storing energy in terms of that potential energy of the electric field that's present there. So if we were going to draw a picture, the simplest capacitor you could have is called the parallel plate capacitor. And so I'm going to write this like this. It's the parallel plate. Parallel, these are two lines parallel to each other. So I'm not going to write the word parallel plate. You're going to see that I'm going to write these things over and over again, parallel, parallel. So it's just silly to write that. I'm going to write parallel plate capacitor. Now this kind of capacitor is just sort of like for discussion. You're never going to see a parallel plate capacitor inside of a radio because they'll just be too physically large. But to get the idea across, you can really understand it really easily by thinking of two big giant plates. So you can sort of think of, here's one plate, literally it's like a sheet of aluminum foil you can think of, right? And then right underneath it, there's another one, right? And it would go something like this, like that. So they're stacked on top of each other and they're not touching. That's very, very important. Capacitors are always going to have two sheets of metal of some kind, right? In this case, we're drawing it as two planes, but they cannot touch. There always has to be a gap, always, always, in a capacitor. And so we draw it with a gap here. And so this gap here, I'm going to draw it like this. That's a distance d, right, between them. And then the capacitor itself has some kind of surface area associated with the top plate and the bottom plate. They have the same surface area, right? And so that is a capacitor, ladies and gentlemen. There's air between them, or you could even bring it into outer space. You don't need any air. You could just put the two plates separated by a very small distance there in space. There doesn't have to be anything between them. And this capacitor can store charge. It seems kind of amazing. It's a very simple device. But what happens is, if you take this capacitor, let's say you built it like this, and you hooked it up to a battery, then you would solder some wire here, and you would maybe connect another wire down at the bottom, and you brought these two wires out and connected it actually to a battery, and the battery can supply a voltage. And you know this, you know batteries can supply a voltage. So I'm not going to draw the symbol of a battery here. We'll get to that in just a few minutes. But let's just say it supplies a voltage, right? It supplies a voltage, right? So let's say this is a 5-volt battery or something. Then what's going to happen is this battery is going to begin to supply electrons over to this plate of the capacitor. Or maybe if I hook the battery up another way, the electrons are going to come out this way and charge up this side of the capacitor. So what's going to end up happening in the net result, no matter how you hook it up, is that this top plate is going to be charged up, because we say it stores charge. So we say, let's say it charges up to positive Q, so many coulombs. I don't know because I don't have any numbers here, but it charges up to so many coulombs. And if it charges up to so many positive coulombs on the top, then the bottom plate must be charged up to the same number of coulombs, but negative coulombs. Because if you think about it, let's just pretend that this battery is hooked up in such a way that the electrons are coming down and then they're flooding into this plate, right? So they're beginning to charge this plate up negatively. They're beginning to charge that plate up negatively. Now, if this entire plate is negative, then what's going to happen up here is that these plates are really close together. So if that bottom plate becomes negative, and these things are made of metal, and remember, metal has a lot of free electrons in there that can be easily induced into moving around. That's why we use metal in our wiring, because we hook a battery and we can easily ask those electrons to move along. That's because metal has a lot of free electrons in the outer shells of the atoms. Plastic doesn't have a lot of free electrons out. They're all bound really tightly, so plastic doesn't conduct any electricity. But if this guy comes up to a negative charge because of the battery that pushed the electrons there, then what's going to happen is this negative charge is going to begin to attract, or I should say repel, the electrons in the top plate farther away. So you're going to have a net positive charge on the bottom there. So you kind of have to use your imagination a little bit, but if these plates have a certain thickness to it, which they always will, if the bottom plate becomes negative, then it's going to sort of repel the electrons in the top plate away, farther up. And that's going to leave, right near the gap there, it's going to leave a net positive charge. So when you're looking at capacitors, the easiest way to think about it is that one of these plates is always going to be charged positive, and one of these plates is always going to be charged negative. Always, 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 right? That's just the way it works. So on a battery, if you look on a battery, you'll see, like if you look on a AA size battery or something, you'll see that one of the terminals has a positive plus sign labeled, and one of the terminals has a negative sign. So if we put that battery, let's just say we put the battery in like this, whoops, like this, and let's say this side was labeled positive and this side was labeled negative, then this would exactly be the situation. This negative terminal is going to charge this up negatively, and this positive terminal is going to correspond to the plate being charged up positively, right? And that's basically what a capacitor is. So you have charge sort of stored there. The battery has delivered charge, and both plates have an equal and opposite charge that's sort of stored there. And then we're going to draw some more pictures here in just a second, but the net effect of that is that in between these plates is going to be an electric field, because you got these two giant charge distributions, one on the top, one on the bottom. So you're going to have an electric field there. And so when you have anytime you have an electric field there, you obviously have potential energy and so on and so on. We talked about the fact that capacitors store or potential energy storage devices. So let's hang on to that because we don't want to throw that away. Now let's look at a side view of what this might look like. So this could be the top plate of capacitor. So I'm drawing a thickness to it because in real life they're always going to have a thickness. And this can be the bottom plate of the capacitor. Right? This can be the top and the bottom plate of the capacitor. Now, we're going to pretend for just a second that we've hooked this up to a battery. I'm not going to draw the battery here because I don't want to clutter the diagram up, but we've hooked it up to a battery, and so you're going to have to trust me a little bit here. The top plate has charged up to positive Q, so many coulombs. And then the bottom plate has charged up to, so many coulombs, but negative coulombs. So you're always going to have a positive charge on one plate and a negative charge on the other, just like a battery always has a positive charge on one side and a negative charge on the other. It's just the way circuits are. You're always going to have that charge imbalance, and that's how the circuit ends up moving electricity around in the circuit. So you're always, when you hook a battery up like that, you're always going to have one side charge positive, one side charge negative. Now, to help you remember that, I'm going to just go ahead and put positive signs up here. So this whole plate has sort of net positive charge, and this plate here has net negative charge, and that's done just because of the battery. So in between, what do you think is going to be happening in between this gap? Now, don't forget, this gap is really, really tiny. I mean, very, very tiny, fractions of a millimeter. So it's huge here, but in reality, the gap between the plates on a capacitor is very small. In between, you're going to have an electric field, and we always said electric field goes from positive, and the arrows are going to be pointing outward from the positive sources and into the negative. So here's your electric field that exists right there, and I'm going to go ahead and put a little label here. This is the electric field. Now, of course, this is not infinite plate. I mean, capacitors aren't infinite objects, right? So it's a little small thing. So in between the plates, you can pretty much take this electric field to be constant. When you start to get toward the edge of the plates, the electric field, if you actually had a magic camera that could look at it, you would start to see that it would start to kind of curve around. I can't really draw this very well on the board, but it would do something like that. And then on this side, it would kind of go in like this, and something like that. Right? So the electric field is going to be doing things like this. But in between the plates is what we're really most concerned about. So we've taken this battery, we've hooked it up to a capacitor, we've charged the plates up, and an electric field now exists between these plates, right? Now, the interesting thing is, if we're going to get into this here in just a few minutes with some pictures, but once you charge that capacitor up, if you disconnect the battery, what happens? Well, you have a positive plate up here and a negative plate here, and if we disconnect it from the circuit, there's nowhere for these extra charges to go, because, I mean, very, very slowly, I guess they'll leak, through the air, and maybe they'll leak across through the plates here if they're close enough together. But in a perfect capacitor, in the vacuum of space or whatever, then the leakage is going to be really, really, really small. So if you disconnect a capacitor that's charged up, it's going to hold its charge. So that's why you got to be really careful if you work on a television, not so much the big televisions that we have now, the flat panels, but the big tube televisions with the giant glass screens, because inside there are very large capacitors, and those capacitors are used as part of the circuitry to generate and to steer the electron beam that's inside of that television tube. And if you turn off your television and then open it up and then begin to start messing around with the capacitors in there, those capacitors probably still have very large electric charge stored in there, and you could easily shock yourself. You got to be really careful working on electronics. Just because you unplug it doesn't mean anything. And I'll give you one more example. If you look even on your laptop computer, or that's probably the best example. Most laptop power supplies, like you plug it in the wall and you have like the black piece there, and then the plug goes into your computer. Well, there's usually a light, some kind of LED light that tells you when that power brick is active. When you take and unplug that power brick from the wall, if you look closely, that LED, you will see, stays illuminated for probably 1 second after you've unplugged it from the wall. But you would expect if you unplug it from the wall, power's gone, light should be out. But see, inside that brick are capacitors and transformers and other things that store electricity temporarily. And so it stores that electricity, and you can see that light gradually go dimmer and dimmer, and that's because the circuitry in there probably has some other circuit path that bleeds out that capacitor. But in a perfect capacitor, if you charged it up, pulled it out of the circuit, held it out in free space, it would retain the charge that's in there. And then you could hook it back into a circuit and bleed the charge out later on. Okay, positive charge on one plate, negative on the other, electric field in the middle. That is how it's storing. And by the way, that is the potential energy, because if I take this capacitor and hook it up in another circuit, and this charge begins to then flow out of this capacitor, I have stored that electricity, and now I'm pulling it out of the bank vault. So that's how capacitors store energy. So in a circuit, we've danced around the concept of a circuit. But let's begin to draw things just to give you an idea of how it would look in a circuit. So in a circuit, you all know that you have a battery, and you all know we're talking about capacitors. So the symbol for a capacitor is very nice, actually, because it looks just like this. It's two little parallel plates. This is a capacitor, and it reminds you of a couple things. It reminds you that a capacitor is basically like two parallel plates, which is what we're talking about here. And the other thing it reminds you of is that these capacitors have a gap in there. So it sort of mentally reminds you, when you look at the symbol, okay, here are parallel plates and there's a gap. In other words, there's no touching here. And this can kind of get a little bit sort of confusing to you a little bit, because most of you guys in advanced physics here, you kind of have an idea of what an electric circuit is. You kind of know that you have to have a full circuit to a battery to have anything happen. So this capacitor has a big fat gap between it. They're not connected. There's no connection in here, all right? So we're going to talk about the mystery of how that works here in just a few minutes. But let me continue on. So here's the symbol for a capacitor, and then over here, let's say we have a switch. And here I'm just going to draw sort of a general symbol that you would see in a circuit for a switch. It's literally what you would think. It's just the circuit can be open or closed. That's the switch. Now a battery can get a little bit confusing. A battery is drawn like this. Notice it looks almost exactly like a capacitor. Almost exactly like a capacitor. The only difference really is that one line is longer and one line is shorter. And you put a plus symbol on the longer line and a minus symbol on the shorter line. And there's really not a great way to remember that, honestly. But you're just going to have to remember it. Sometimes you might see, if you're looking at a circuit, you might see a bunch of these things like drawn like this. But always, 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 you're going to have a long line on the top and a short line on the bottom. And always, 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 the positive terminal is the long line, and the negative terminal is always the short line. So that's just sort of a universal truth. And that's just something you're going to have to remember. So what this means is that when this switch is closed, this battery is going to begin to supply electric current in the circuit. But you might ask yourself, well, how can it do that if there's a giant big open circuit right there inside the capacitor? How can any electric current flow? Well, the reason it can flow, when you think about it, is because as soon as you shut the switch, the battery has no idea that there's an open circuit right there. I mean, what's going to happen is the electrons are going to attempt to come out, and they're going to see, and they're going to go and follow the path of least resistance. And what is going to happen is that these electrons are going to flow out of this negative terminal, and they're going to come over here, and they're going to begin to charge up this capacitor. And depending on the value of the capacitor, if I have a very large capacitor, it can store a lot of charge. If I have a very small value capacitor, we're going to talk about the values in a minute, it can store not so much charge, just a little bit of charge. But eventually, I'm going to put enough electrons in there where we can't store anymore. And after that point, the electrons are going to stop flowing here because there's nowhere else for them to go, because they can't go into the bank anymore. So if there's no charge here at all, then when I shut the switch off, the electrons are going to begin to flow. This is going to charge up negatively on the bottom, and this is going to charge up positively. It's going to match the battery terminals right here, there. And eventually, I'm going to fill up that bank vault full of charge, depending on how I've constructed my capacitor. And when it's full, it's full. You can't hold anymore. And then it's going to stop, and this current in the circuit is going to cease. But up until that point in which everything stops, there is an electric current here. So even though there's an open circuit there, there's no connection between them, the current can flow for a short period of time until the capacitor charges. Until the capacitor charges. If this capacitor were replaced by a wire, just connecting the two, then yeah, you'd have current going around and around forever until the battery died, right? You would have everything going around and around in an electric circuit like this, but because you have this capacitor here, the current can only flow for a short time until the capacitor is charged. And that's basically sort of the function. And you could disconnect the capacitor and boom, you have sort of like a little storage device. You've got electric, charge stored in there. So I've already said all this stuff, but I'm going to write it down. So this is the capacitor. This is a switch. And I'm mainly teaching you this so that you can get an idea of the symbols. And this is a battery. And you have to understand that the battery looks just like a capacitor, except one line is longer, one line is shorter. Positive terminal is always on the longer line. Negative terminal always on the shorter line. All right? And this battery supplies a voltage, voltage V. Now the other thing is I need to bridge the gap a little bit between talking about pure electromagnetic theory, which is what we talked about before, Gauss's law, electric fields, all these things. Now we're starting to talk about circuits. Before we always talked about a potential difference, voltage difference in an electric field between 2 points, delta V, the difference in potential, right? Nothing is different here. It's just that when you're writing circuits, you don't want to write delta V everywhere. Delta V here is the change of potential across the battery terminals there. You don't want to write deltas everywhere. You don't want to write delta V everywhere. So basically you just know that when you're talking about circuits and you see a voltage V, it always means the change of potential. In fact, anytime you see voltage, how many volts, between, in a circuit somewhere, it's always the change of potential between some point in the circuit and another point in the circuit, always. In fact, that's the definition of the electric potential and sort of the voltage. It has to be talking about between 2 points. Here, it's the terminals of the battery. But we'll talk about later when we're talking about more complicated circuits. You could take a voltmeter and put it between any 2 parts in the circuit, over here, across this piece of the circuit, across that piece of the circuit, and you're measuring the potential difference in volts between those 2 points. But I'm just telling you that when you see it in circuit, you're not going to see delta V, you're just going to see the letter V, but that's the same exact thing. It's the potential difference between the battery terminals. Okay, so let me redraw this one more time and say a few more things. I don't want to clutter up my drawing. So this guy is connected here. The battery terminal is always positive on the long line and negative on the short line, right? So once the switch is closed, let's go ahead and draw it closed, like this. So we close the switch. What's going to happen in the net the net effect of everything after you let a long time pass is that this capacitor, which has a capacitance C, we'll talk about it, how to calculate that in a second. This terminal charges up to positive number of coulombs, and this terminal charges up to negative coulombs. And it's easy to know what is what because it has to be the same as the battery. If you have a positive terminal up here, then this terminal must be positive. If you have a negative terminal here, then this terminal must be negative. And the value of how many coulombs is stored here is going to be dependent upon the capacitance that we're going to calculate in a minute, and it's also going to depend on the voltage that this battery supplies. In other words, the battery is going to supply the current, so obviously how much charge stored depends on the battery. It's also going to depend on the capacitance C, which is how your capacitor is constructed. That's going to determine actually how much charge is in there. Now, there's a couple things I want to explain. Your book may not explain this early, but you got to understand in the deepest part of my body, I'm an electrical engineer. I mean, I love physics, I have a degree in physics, but I'm an engineer. So I'm trying to teach you these practical things that your book may not tell you in a physics book quite so readily up front. I'm going to teach you a little bit about circuits earlier than in your physics book is what I'm really trying to say. So let me tell you a couple of additional things. And the reason I'm going to tell you these now is because it's going to help you as you start reading the other sections in your book because of these things I'm telling you. Point number one. When you have a circuit like this connected, like this capacitor is connected to the battery terminals, this voltage V is, let's say it's 10 volts, whatever. Could be a 10 volt battery there, a 9 volt battery there. Because it's connected directly across the capacitor, if I measured the voltage between these 2 points, like if I've got a meter out and stuck it across the capacitor, it would also be 10 volts, let's say. Let's say it's a 10-volt battery. Then it would be 10 volts across here. In other words, it sounds so simple, but you can get really confused when you get into more complicated circuits. But if you have a battery source that's giving so much voltage, potential across the terminals, and it's connected directly to something like this, then the voltage across this guy has got to be exactly the same as the voltage across the battery because they're physically connected together along a wire. And that's sort of the case. So later on, let's say, you know, I'm getting ahead of myself a little bit here, but let's say I added another capacitor here. And let's say I added another capacitor here. And let's say I added another capacitor here. I added like 3 capacitors. And the question on your test was, well, this is a 10-volt battery. What is the voltage across these terminals? You see, you might be tempted to do some complicated calculation with all these capacitors, and we're going to talk about lots of different kinds of problems later, how you could simplify this significantly. But you need to realize that by looking at the circuit, you know that this capacitor is directly connected to this battery. So the voltage, the potential difference, has to be exactly the same because they're physically connected together. It doesn't matter what's over here. It's just that when you're talking about voltage, if you're connected to the source like that, the voltage that you see at those terminals way at the end of the circuit is exactly the same as what you see across the battery. That's something that's important for you to know. Now the next thing I want to talk about is the charge-up process a little bit. So what's going to basically happen when you turn the switch on is a current is going to start to flow. And obviously it can't go across this guy, but it can pile up and begin to be stored inside of this guy, and the electric field begins to be present there between the capacitor plates. So what's going to happen at the moment you switch on that circuit is a relatively high current is going to start to flow. But as the capacitor begins to charge, it's going to begin to fill up, and so it's going to begin to be able to accept less and less charge because it's going to be getting closer to full. So as it gets closer and closer to full, the current is going to slow down, so to speak. It's going to begin to bleed off until eventually no current is flowing at all. So I don't feel the need to draw a bunch of graphs here and confuse the situation, but I just want to tell you that when you turn the switch on, that current is going to begin to flow. And then as the capacitor charges up, that current is going to go down, 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 down because the capacitor is filling up. And then once it's totally full and it can accept no more charge, then the current goes right down to 0. Or basically, it's so close to 0 that it might as well be 0. So no more current flow. So if you let this guy charge up fully, you'll see the 10 volts across the capacitor. And if you had a current meter in here, like if you put a meter in here to measure the current, you would see no more electric current flowing because this capacitor is fully charged. All right? That is basically all I wanted to say about that. Now, let's get a little bit into the bread and butter of how to calculate capacitance. So we know that if we put a potential difference across a capacitor, we know that it charges up to have charge piled up on the plates. We know that. But what we want to know is how to calculate that and how it's related. So basically, without further ado, we're going to answer that question now. The main equation that deals with capacitors is the following. So the capacitor charge, right, is equal to the following. Q, which is the Q that's piled up on the plates there because we've stored it, is equal to the capacitance, which is the value of that capacitor, times the potential across the terminals. That's what you need to know. It's a very simple algebraic equation. There's no integral here, there's no derivative, it's very simple. If you want to know how many coulombs are stored on this plate as a positive charge, and of course they would have the negative number of coulombs down here, you just need to know the value of the capacitor, right, that we're going to show you what that means in a minute, multiply it by how many volts you have. You're always going to be dealing in volts. You multiply those things together and you're going to get coulombs, which is a unit of charge that we're always talking about. So for the units, let me switch colors here. So for the units of capacitance is called a farad. it's called a farad. So 1 farad, right? And that's equal to, let me show you something here. If I solve this for capacitance, the capacitance is equal to how much charge I have on the plates divided by the voltage that's applied, right? So 1 farad is going to be the number of coulombs. We write it, a farad, as F, and that's going to equal to 1 coulomb per volt. Coulomb per volt. No surprises. So 1 coulomb per volt. But you never write coulomb per volt, you just write farads. Now, of course, you know, just like a lot of other units in electricity and magnetism, a farad is a very large unit of capacitance. I mean, a farad capacitor might be the size of this room. So I've never seen a farad capacitor. Most capacitors that you look at, all capacitors that you look at inside of electronic devices, you know, in your computers or in your radios, they're nowhere close to a farad. A farad's huge. So you're going to be having microfarads is usually the unit that you're talking about, 10 to the minus 6 farads, or even nanofarads or picofarads. Maybe you might see a millifarad capacitor for a big, you know, project and, you know, some kind of thing that's not in a consumer device, but something you might have in a lab somewhere. But definitely never a farad capacitor. So if you ever calculate a capacitance that's a whole farad, then you probably did something wrong, or the problem was just set up to give you a huge answer for no great reason. But most capacitors that you see are always going to be microfarads. So you're going to see this a lot, microfarad. You're going to see that a lot. Okay, so just like we said before, it's the same thing with coulombs. You never hardly see a coulomb either. You might see a millicoulomb or a microcoulomb, but you hardly ever see a whole coulomb of charge written down there. Okay, now what we're going to do now is erase the board, and we're going to go back down memory lane, talk about Gauss's law to show you how you would actually use this stuff and calculate the capacitance for like a parallel plate capacitor. You know, if you know the charge on the plate and you know the voltage, great, you can calculate that, but there's a couple little things I want to talk about. Before we get to that point though, I want to kind of take you on a little bit of a tangent, and it's a tangent that's going to be very useful for you to understand. I didn't learn this until way later in my studies, you know, a couple years maybe after what you're studying here in this course. It's very, very important though. Here's the deal. In real life, when we have circuits, we know that the electricity in the circuit is the electrons flowing in the circuit. We know this because, you know, it's called electricity. So electrons are the things that are moving. And that's just because the atoms, like we said, have a lot of free electrons in their shells. So they can move around and all of that stuff. Now, here's the deal. You can look at this circuit, you can label positive and negative, and if you wanted to, you could totally calculate the electric current in terms of the electrons that are actually flowing here. That would be fine to do. But because electrons are negative, you would have a bunch of negative signs running around in every equation you ever wrote down for electric current. You would always have a negative sign there, and it just gets cumbersome. So some smart people a long time ago decided that when we're talking about electric circuits, we're not going to talk about negative current, the electron current. We're going to instead talk about the positive kind of equivalent current. And the easiest way to think about that is with a picture. If you have a bunch of atoms here, this is the nucleus, one proton, let's say, and here's a free electron there. And here's another proton in this wire and another electron. Here's another proton and here's another electron, right? Now we know that when we hook the battery up to this wire, you have to pretend, use your imagination and say this is a wire. When we hook the battery up, we know that this electron jumps to this atom, and then this electron jumps to this atom, and then this electron jumps and jumps, and they all end up jumping in a chain reaction all the way back around to the battery. And that's how an electric circuit actually works, right? That's great. But that is the negative electrons that are flowing. But if you think about it for a second, for every, let's say I have an atom here with my electron. If my electron leaves this atom, I have left behind a positive nucleus or a positively charged nucleus. So for every electron that moves that way, it's equally mathematically the same as sort of a positive charge flowing in the opposite direction. It might be more, you know, kind of easy to understand if you just think about one single atom. If you have one atom and here's your electron, if he jumps away, that current is sort of flowing that way. It's exactly the same as an equivalent positive current flowing in the opposite direction. And that positive current is what we actually use in our equations and in our electric circuits and all of that stuff. So I've been careful so far to talk about electrons coming out here and charging up capacitors, but in a few sections we're going to talk about the definition of the electric current, which is what we're sort of hinting about right now. And what I'm trying to tell you is that electric current is always going to be positive current coming out of this positive terminal of the battery. So it would always be coming out of the positive terminal of the battery. Even though protons or positive charges don't actually flow in a circuit. We know this physics-wise. But mathematically it's the same exact thing. And I think if you think hard enough about that and visualize it, I think you can understand that if you have a whole string of these atoms and all the electrons are jumping from one guy to the next over this way, then mathematically it's exactly the same thing as pretending that positive charges are going the other way, even though they're not, right? So when we calculate the current, we're going to always be talking about the positive current coming out of the positive terminal. The positive current coming out of the positive terminal, even though in real life we know that it's not actually the positive charges moving, it's the negative charges going in the opposite direction. Okay, I think that's enough of that. So let's go ahead and erase the board and talk a little bit more about how to calculate the capacitance. So what we're going to do is just move right along here. So how would we calculate the capacitance? Well, we said, here's how you calculate it. If you know the charge on your capacitor and you know the voltage that you apply, well then great, you can calculate the capacitance. But that doesn't really help me too much if I have a parallel plate capacitor. I mean, yeah, I guess I can measure the charge on it and then I know what voltage I'm applying to it, so you can always calculate the capacitance that way. But if you had another arrangement, let's say you built a cylindrical capacitor, which we're going to talk about in a minute, where instead of two flat plates, it's wrapped around, the two things that are parallel to each other are kind of wrapped around like that. How would you calculate the capacitance of a different configuration? So the general way that you do it, it is exactly this. It's just that you have to take a few steps here. To calculate the capacitance, you have to do the following. Well, you don't have to do the following, but you're going to end up following the same steps. So we know that the charge is equal to the capacitance times the voltage applied. So the capacitance is definitely going to be equal to the charge divided by the voltage. So this is what we need to use. It's just that usually you don't really know exactly what potential is going to be over there, and so unless you're building a circuit to actually measure it. I'm talking about, when I say how to calculate the capacitance, I'm talking about if I draw a picture of a capacitor, how would I calculate it? I mean, of course you can build it in the lab and measure the capacitance, but I'm talking about how would you mathematically calculate based on your design of a capacitor. So here's what you're basically going to do. And I'm only going to do one simple example like this. You may be asked to do this on a test, but you're not going to use this too much in real life, so I'm not going to dwell on it. The first thing you do is you assume a charge Q exists on the capacitor plates. Right? So you have to make an assumption there. So you start at that point, and then you calculate the electric field between the plates, because you know there's going to be an electric field between the plates, by Gauss's law. And just for reference, because you may have not remembered that off the top of your head, Gauss's law is the permittivity times the surface integral of the electric field dotted through dA, and that's going to equal to the included charge. And we'll do an example to show you. But basically, if you know the charge, then you know this, and if you know the geometry, you can sort of figure out where the electric field is going to be, and you basically try to calculate the electric field. Now, once you know the electric field, then you can calculate this potential, because the electric field, remember, is related to the potential. So we using E, we calculate the potential across the plates. And how do we do that? If you remember, the potential is going to be equal to, the change in potential is going to be equal to the final value minus the initial value of the 2 points that you're actually dealing with, which is going to be from one plate to the other, because I'm trying to find the voltage across the 2 plates. And that's going to be equal to negative integral from the initial to the final position, which is across the plates, of the electric field dotted with ds, which is just the path. That's going to give you the voltage. And then at the final step, you know what Q is because you assumed what Q is. You've calculated what V is, so then you just say the capacitance is equal to the charge you assume divided by the voltage that you calculate. So like I said, I mean, you can build the capacitor and you can hook it up to a 10-volt source and you can measure the charge on the plates and you can calculate the capacitance. That's not what this is really intended to show you. This is trying to say, let's design a capacitor. Let's design it like a battleship, you know, total weird shape to it or whatever. How would we calculate the capacitance without actually building it? So you make an assumption. You say, okay, I have 5 coulombs of charge on each plate. I calculate the electric field that's between those guys, and I use Gauss's law or whatever other tool I have to figure out what the electric field is. Once I know the electric field, I can calculate the potential across the plates because I can just integrate the electric field between those 2 points. And we covered all of this in Volume 1, so all of this is stuff you already know how to do. Once you know the voltage across the plates and the thing that you assume there for the charge, then you can just simply divide the 2 things together and calculate the capacitance. So I think it's going to be nice to show you this with an example. And again, we're going to learn about a few different configurations of capacitors here. I'm only going to derive the capacitance for the first configuration, the easiest one, the parallel plate capacitor. Because you could derive it for all the other ones, but really it's diminishing returns. Once you know how to do it for one of them, it's good to know you're not going to be doing this very often unless you're maybe on a test. But in real life, you certainly wouldn't be doing this. Because when you buy a capacitor off the shelf, it tells you what the value of the capacitance is. This is sort of more of a theoretical thing to build your foundation and sort of teach you where this stuff's coming from. So let's look at the parallel plate capacitor. Parallel plate capacitor. And just like we drew a picture before, it's basically just like you would think. It's 2 plates. We draw it kind of big so we can see here. It's 2 plates like this. And the top plate has positive charges, let's just say, because it's charged up. We're going to make an assumption. That was step 1, remember? Step 1 is we assume we have a charge on the plate. So we make that assumption. And so we say, okay, this is positive Q. And we say, okay, this is negative Q. Okay, that was step 1. And step 2 is basically, or step 1 I should say, after we make an assumption that the plates have a certain charge on it, is to try to calculate the electric field. So let's go ahead and do that. We're going to use Gauss's law, which is the electric field dotted with dA, which is our Gaussian surface, and this is the charge enclosed. So there's a couple things we need to add to our drawing in order to get this. We know just from the previous drawings that there's an electric field here. I mean, there has to be. There always is inside of a capacitor because you have these charges that are piled up on the plates. So there's an electric field inside there, and in order to calculate that with Gauss's law, we're going to have a Gaussian surface. Now you have to think about this and remember that this is a parallel plate capacitor, so it extends out of the board. It's a 3-dimensional object. So here's one plate, there's another plate underneath it, and it kind of goes into the board there, and so it has a surface area to it. So this top plate has a surface area A, which is the planar area, and the bottom plate has exactly the same area. So this is the area. And so if I'm going to calculate a Gaussian surface, the best one, or to use a Gaussian surface, a really good one is this one right here. I'm going to cut this plate kind of in half. I'm going to come over and I'm going to go right into the middle of my electric field. I'm going to come back up. And the reason that's a good plate is because in a minute we're going to be integrating this electric field through this Gaussian surface area that I have. But there's no electric field pointing out through the sides here. Now in a real life capacitor there would be those fringing fields around the edge, but when you're doing these theoretical calculations like that, you assume that those fringing fields are very, very small, so they don't count. So there's no field going through the sides. There's no field inside of this metal. We talked about that from before. There's no electric field inside of the metal. The only field is really out here, and it's cutting across perpendicular to our Gaussian surface. So this is a great one to use. All right, so let's go ahead and do it. So what we're going to have is, this is the permittivity. The electric field is a constant inside of here. You know, if you go back and look at the derivations of the parallel plates, when you have two parallel plates like that, the electric field, assuming that these things are really close together compared to how big they are, then the electric field is going to be relatively constant in there. So you can pull the electric field out, and that basically simplifies the integral totally. All you're left with is some integral over the area and equal to the charge enclosed. But inside of this Gaussian surface, this plate that's extending out like this has a total charge of positive Q. So I'm going to put positive Q. Negative Q on the other plate has nothing to do with it because it's not inside the Gaussian surface. Only what's inside the Gaussian surface is the charge enclosed or included. So this integral here over dA is nothing more than the surface area of the plate there that you know because you're building it. And so you have this result right here. So you have the permittivity times whatever the electric field is times the surface area of the plate is equal to the charge. Now this isn't the answer. This is just really allowing you to calculate you know, sort of the electric field there. So let's stop at this step. We know what the charge on the plate is there. And so remember, the end result of where we're trying to go is the capacitance is equal to the charge on the plate divided by the potential. We know what the charge on the plate is in terms of all of our other variables, so let's stop there. The next step is let's use this electric field, or the electric field that exists, I should say, between there, to calculate the potential. So let's go and have a negative integral from over the two plates, E dotted with ds. So basically I'm going to take this electric field and I'm going to integrate from one plate to the other. I'm going to integrate this electric field over a path from one plate to another, and that integral is going to yield, the negative of that number I get is going to be the voltage that's basically across the potential difference between those two plates. So if I'm going from one plate to another, I can simply say that this plate is at 0, and I could say that this plate is at D because these plates are spaced apart by D units. We talked about that in the very first drawing. So I can go from 0 up to D. And so this is a very simple integral because this is a constant. So you have negative E integral ds, which is just a linear integral over distance, 0 to D. Okay? And so what you're going to end up having here in the end is negative E D. So the potential across is equal to negative E D. And I think you can see that this integral does reduce to D because this integral is basically just have a 1 here. So you have a dummy variable s evaluated at D minus 0. So you're basically just going to get D. So basically all you've done here is you've added up the distance between 0 and D, and of course you get D, the distance that you had to begin with. This is a simple integral here. So you have this guy. So we know what the charge on these plates is in terms of everything, and we know what the potential is across the plates that we've calculated. And so when we calculate the capacitance, Q over V, we have epsilon naught times E times A from here over this guy, which is ED. And I could carry a negative sign there, but really we're only for this particular calculation, we only care about the absolute value of the potential. Because if I put a negative sign here, you remember how we talked about this in the last section. When you have negative and positive in terms of potentials, it just depends on what you're looking at as your initial position and what you're looking at as your final position. It just means that one side is higher than another in terms of voltage. If you have a negative here, you know, I could put a negative here, but then it would give me a negative capacitance, and you never have negative capacitance. So we basically just strip the sign out, and when we're doing these calculations of the potential, we're only really interested in the absolute value of the potential difference between the two. Another way to think of it is, I did my integral like this. If I had flipped my limits of integration around and integrated from top to bottom, I would have got a positive number anyway, and that's exactly what I want. So the order of integration isn't really going to matter for this. So you can see that the electric field cancels. And so the capacitance of a parallel plate capacitor is the permittivity of free space multiplied by the area of the plates of one of these plates divided by the distance between them. divided by the distance between them. And that's it. You'll see this in your book. This is the parallel plate capacitor. It's the capacitance. So if on a test you have a problem and it's like you have a parallel plate capacitor, the surface area of each plate is equal to so many square meters, and the distance between them is so many millimeters. Of course, you have to convert everything to meters. Divide them, multiply by the permittivity, boom, you've got a number in farads. That's the capacitance of that capacitor, right? Now, one more thing I want to point out. Well, first I want to review a little bit, and then I want to point a couple things out. All we did is we said, okay, we have a charge on our capacitor, equal and opposite, like always. We use Gauss's law over a Gaussian surface that only includes one of the plates, and the electric field can come out because it's constant in there. And so what we're left with is this guy is equal to the charge. So we hold that in our back pocket, and then we go and look and see, all right, if we're going to calculate the potential between the plates, we integrate over the distance, the electric field dotted with ds. But again, because the electric field's constant, we can pull it out, and this integral reduces down to something really simple. So now we have the potential across, and we have the charge. We divide the two, we calculate the capacitance. For any other configuration in real life, the electric field may not be perfect. Well, even in this case, a real parallel plate capacitor, the electric field's not totally constant inside, so pulling it out of the integral isn't really legal in real life. But it's a very good approximation whenever you have plates that are really close together and very large. So that's what we're going to go with on this. It's sort of a theoretical calculation. Just think back to Physics 1 when you had your massless pulleys or your frictionless ice or something like that. So that's what we're doing here. The other thing I want to talk about is when you look at the capacitance here, if the distance goes down between the two plates, the capacitance goes up. Right? If the distance goes down, the capacitors goes up. And also, if the distance goes down, if you look over here at this equation, if the distance goes down, then the electric field also goes up. Because if you solve this for electric field, you're going to have a D on the bottom. So what I'm trying to get at is if you have the distance between the plates goes down, electric field goes up, so a higher intensity electric field in there, and capacitance goes up, so you're allowed to store more charge in that capacitor if you can get the plates closer and closer together. And if you can also make them physically larger, they can also hold more charge because there's more atoms in there to store the charge. And if they're closer together, you can get that electric field a higher intensity, and you can also store more charge in there because of that, because the electric field is inducing, this electric field is inducing these negative charges on the other side here. So the higher you can get that electric field, the more charge you're allowed to really store there. Another way to think about it is, if you can get a higher electric field inside of this capacitor, it'll have more potential energy because the field will be stronger. Okay? So what we're going to do now, we've given you the equation for a parallel plate capacitor, and I'm going to draw a few other kinds of configurations of capacitors that are going to be in your book, and we're going to give the values of the capacitance for those. Okay, so let's write down the equation that we just derived for a parallel plate capacitor, and then we'll write down a few other configurations. So for parallel plate, right, the capacitance is equal to the permittivity times the surface area divided by the distance between the plates. So this is sort of one to remember. And notice that we derived it using Gauss's law. So if you were to write down any configuration of two plates, maybe spherical, cylindrical, however you want to do it, you could use Gauss's law in exactly the same way to calculate the capacitance of any of those configurations. You would assume a charge on there, set up a Gaussian surface, calculate the electric field, calculate the potential, divide the charge by the potential, and then you get your capacitance out. And your book does that for some of these configurations, but I'm not going to derive every one of them because I don't think it's a great use of time. I think to know how to do one of them tells you where this is coming from. The rest of it should just sort of be given, I think. Cylindrical capacitor. Now, cylindrical capacitor you actually do see quite a bit in, in real circuits. So what you would have here is, let's say you had a cylinder, something that looked kind of like this, has a length to it, right? And so here is another central core kind of. So basically you've got sort of the same thing as the parallel plate, it's just that it's wrapped around on itself. You've got an inner surface and an outer surface, and they're separated by a distance. So this distance is d, right? That distance is actually, the way I want to label it is a little bit different. It is distance d, effectively, it's the same sort of thing, but I want to write it a little bit different. I think it'll make it a little bit clearer. If you were to look at this top down, then you would have an inner guy and you would have an outer guy, right? And so let's say, you know, the inner guy might be positive charge, let's say, and the outer guy could be negative charge, or it could be backwards. Or if it's an oscillating circuit, it reverses back and forth, positive, negative. Inside gets positive and negative every cycle and so on. But that's basically what you would have. And then so, let me switch colors here. The radius of this inner guy, we're going to call A. And the radius of this outer guy, we're going to call B. And we're going to say that this inner guy has a charge Q and this outer guy has a charge of negative Q. And we're going to say that this capacitor has a total length of L. So that sort of describes the geometry. Just like for the plates, all you needed was the distance and the area. Here you need to know sort of the inner radius, the outer radius, and the length to fully describe the geometry. And once you have that, the capacitance that you get is going to be 2 pi times the permittivity epsilon times the length of the capacitor divided by the natural log of B over A. So you know the distance is B divided by A, take a natural log, the length divided by that quantity times these numbers, that is going to give you the capacitance in farads. Again, it looks complicated, but if you were to set up a Gaussian surface around and do exactly what we did before, this logarithm would pop out as part of the integration that happens there, and you would see it there. So that's, don't be surprised, like, why is there a logarithm here? It's as a result of the integrals that you end up doing when you do that derivation. But I'm not going to derive it for you because, number one, you're really not going to be using this in real life too much. You're not going to be really deriving capacitance too much anyway in real life. And the second thing is, I think it's more instructive just to sort of know where it comes from and sort of that you can at least say that you know how it's derived. And then if you really wanted to dig into those details, I'm confident that with Gauss's law you could figure that out. And it's a better use of our time just to continue moving on. So another kind of capacitor you'll probably see in your book is a spherical capacitor. It is a spherical capacitor. And it actually looks exactly the same because, you know, but it's not the same, but it looks the same if you draw it on a piece of paper. Because if you have two concentric spheres, instead of a cylinder where they're nested inside, let's say you had a central sphere and then an outer sphere. Again, you have a separation between two surface areas is really all you need to make a capacitor. And let's say that, this inner radius was again A and this outer radius was again B. There's no length to it because these are spheres. And let's say this is, charged up to positive Q. And let's say this on the outside is negative Q. So the capacitance in that case would be equal to 4 pi times the permittivity times A times B over B minus A. That's the capacitance of a spherical capacitor. Again, it's just the geometry. A times B divided by B minus A times these constants out in front. It kind of makes sense that you have a 4 pi here because spheres involve, 4 pi r squared, for instance. And then over here, 2 pi kind of makes sense because you have some spherical, some cylindrical stuff going on there. And you would see all that fall out of your derivation. Now, the final one that we're going to talk about is an isolated sphere. Now, this one's a little bit interesting to think about. If you have just an isolated sphere, for capacitors you have to have two plates. But it turns out that if you have like an isolated sphere here, if it's not connected to anything, you can charge it up and it'll hold a charge, that can be discharged at a later time. So it behaves as like a capacitor. And the easiest way to derive it is just to sort of take this result and make the second dimension, B, go out to infinity. So you can sort of think of an isolated sphere as having this central sphere, where the outer sphere is so far away that it really isn't even relevant. So if you start off with what we had before, the capacitance is 4 pi times the permittivity times AB divided by B minus A. And if you take B going to infinity, then what are you going to have as a result? What are you going to have as a result? You want to basically take the limit as B goes to infinity. But if you do that, infinity is going to be on the top, and then infinity is going to be on the bottom, and so it's going to be a little bit hard to do. So the easiest way to do is to rewrite this capacitance as the following: 4 pi times epsilon naught. If you divide B on top and B on the bottom, then what you'd be left with is A over, and then what you would have on the bottom is 1 minus A over B, right? Because if I divide the top by B, then I'm just going to be left with A. And if I take this denominator and divide it by B, which is totally legal to do, then I'm going to have 1 here, and I'm going to have A over B here. This is sort of a trick that you learn when you solve simple limits. So if I take the limit as B goes to infinity, then this term is going to drop to 0. 1 minus 0 is just simply 1. And so the capacitance that we're seeking here is 4 pi epsilon naught A, which is basically the distance from the center of this guy out to the edge. And so generally when you're talking about a sphere, you want to talk about the radius, so you just relabel that 4 pi epsilon naught R. You know, you can just use these formulas in the book, it's fine. It's just I try to give you a little bit of an idea where they're coming from. If you take a sphere, a spherical capacitor, and take that second, the dimension B as the second part of the capacitor way off at infinity, and just do the simple limit right here, then what you'll get is this capacitance of an isolated sphere. So if you know the radius of a sphere and how, basically the geometry of it from the radius, then you can calculate its capacitance. And it can behave like a capacitor. You can hook it up and charge it up, and it'll maintain charge, and you can bleed charge off like that. So this is sort of the end of the section here. We're going to work a lot of problems in the next section. We're going to get you very comfortable dealing with capacitance and calculating how many farads a capacitor is and understanding what it really means more than just sort of the theoretical things that we've talked about here. But a parallel plate capacitor is basically going to be related to the surface area and the distance between the plates. The capacitor of a cylindrical capacitor, you see this a lot in real circuits because if you look at a lot of those capacitors, they look like cylinders. And again, it's going to be related to the length and also the dimensions of the inner and outer. Same thing here, the capacitance is going to be related to the dimensions of the inner and the outer sphere, and here it's going to be related to the dimensions of R, of the sphere that you have. So what I'm trying to say here, by pattern, is that the capacitance of any object, or any kind of arrangement, is always just going to be related to the geometry of how you've arranged it. The capacitance of a parallel plate, it's only related to geometry. This is just a constant. The capacitance here, it's only related to the geometry, in other words, the length, the width, the height, how it's all set up. It doesn't have anything to do with anything else other than how you've constructed it. And the same thing here. So you can calculate them all with Gauss's law. You can look in your book for that detailed derivation. My advice to you is just to understand how this one was calculated, to know basically how you would go about calculating the rest of these by choosing your Gaussian surfaces. But I would spend most of my time understanding the fundamentals of capacitance and what it means, and then on into the next section of this DVD course where we're going to work a lot of problems to really teach you, how to use capacitance and how to calculate and put some numbers to some of these equations. I'm Jason. I hope you've learned something from this section. Let's go on to the next section and work some problems dealing with the calculation of capacitance.